Sun Tzu wrote his famous Art of War over 2,000 years ago. In it, he discusses the importance of intelligence and the efficient use of resources in combat. These war tactics are still relevant today. The Air Force Research Laboratory has challenged our team to modify a JetCat P100RX turbojet engine in a way that will increase its thrust-to-weight ratio without affecting its thrust-specific fuel consumption or its propulsive and thermal efficiencies. Increasing the thrust-to-weight ratio will increase the overall performance and maneuverability of whatever aircraft the engine is installed on. This will result in increased combat capabilities and more efficient equipment for the military. A turbojet engine can be broken down into three sections: the starter and inlet cowling, the rotational components and combustor, and the nozzle. The rotational components can spin at speeds in the hundreds of thousands of RPMs and require extreme precision in manufacture. Due to their dangerous nature, our team decided against modifying the rotational components and instead chose to replace the material of the inlet cowling and redesign the exhaust nozzle. The original inlet cowling was manufactured from stamped and painted aluminum that had a mass of 32 grams. We chose to 3D print a replacement cowling for polylite PLA, resulting in a final mass of 9 grams. This gave us a 28% weight reduction for this part. The engine generates its thrust by intaking air through the cowling, expanding the air via combustion, and guiding the heated exhaust out through the nozzle. Due to rotating components mentioned earlier, the exhaust obtains a swirling velocity. This swirl results in components of the air velocity being perpendicular to the engine's movements, which does not generate thrust, essentially giving us wasted energy. By incorporating vanes into the nozzle design to correct this swirl, the energy will be redirected into the desired direction, increasing the total thrust output. Since we wanted to incorporate vanes, we decided to manufacture a nozzle out of a 3D printable ceramic silica. Producing the model through 3D printing provided us with seemingly infinite nozzle design options that cannot be produced through any other feasible manufacturing method. To manufacture a solution that our team is putting forward, the cost of producing a single nozzle would be about $19.32, where the price per nozzle could become much lower if materials were bought in bulk. Moving forward, the next steps of this project will be to continue the iterative design process on the inlet cowling to further reduce its weight. Additionally, more work can be done on the manufacturing of the nozzle, specifically looking at the shrinkage as well as the slumping and warping that occur during the sintering process. Finally, refining the CFD model to use it as an optimization tool will allow for rapid prototyping of the nozzle.